Hi everyone, my name is Chip, and today I'm going to talk about real-time machine learning. A little bit about my background. I come from a very non-tech background. I have actually published a few books before I switched to doing computer science, and I started with product management. And then I work in machine learning at Prima Netflix. I'm currently with Snorkel AI as a machine learning engineer and open source lead. I'm also teaching machine learning system design at Stanford. So as a motivation for this talk, I just want to bring to attention TikTok. So who here has heard of TikTok? Because I can't see anybody's hand, so I'm just gonna assume that everybody raised their hand. TikTok is probably one of the biggest social phenomenon in the last few years. It totally eclipsed like what came before it, like Vine, Snapchat. One adjective I keep hearing people mention when I talk about TikTok is that it's incredibly addictive. There are many reasons why TikTok is so addictive, but I think one of the reasons is the technology. The companies that own TikTok back then has built an incredible infrastructure that allows them to do real-time machine learning. It means that they are able to learn user preference in real time. So if you watch something right now, they can learn what you have just watched and choose like what to show you next. And the recommendations are really good, giving users an incredible scoring experience. So TikTok is one example to show how powerful real-time machine learning is. And this is what we're talking about in this talk. So there are two levels of online real-time machine learning. One is like online predictions, and another is online learning. But before we start, let's just take a step back and try to see like what does real-time means. You've really heard like a lot of philosophers saying like there's no such thing as time. And if you talk to software engineers, they're gonna tell you that like there's no such thing as real time, because no matter how fast a system is, there's always some latency. Whether it's like millisecond to nanoseconds, there's some latency. And some people like to be technically correct, they would use term like near real time or near live. And this term is like kind of not very natural. So for as this talk, I'm using real time to address to encompass all of that. So there are two levels of real-time machine learning. First is level one, are like predictions, when the system is able to make predictions in real time. And in this case, real time is defined to be like from milliseconds to seconds. And the level two is online learning, like the system is capable of incorporating new data and updating the model in real time. So in this case, real time is defined to be in the order of minutes. I also want to clarify what is mean to model and system, because both of them are terms that have a lot of meanings. So model is machine learning model, for example, BERT, GPT-2, and system is the encompassing all of that, including interface, infrastructure, data compute. So let's go to the first level online predictions. So if you have built systems for users, you will notice one thing, that latency matters a lot. There have been many experiments conducted to show how important latency is. There are two examples that I really like. One is by Google, and this shows us like if you increase latency from 100 to 400 milliseconds, can reduce searches like up to 0.6%. And another is Booking.com, like for 30% increase in latency can cause like 0.5 conversion rate. And conversion rate is tied directly to revenue. So 0.5 conversion rate is actually can reduce a lot of revenue. And like no matter how great the machine models are, like if it take just milliseconds too long to make predictions, user are gonna click on something else. So you have noticed like in the last decade, the machine learning research community have taken on this approach, like bigger, like better performance. So at first, like you think like 1 million parameters was crazy, but then they went to like 1 billion parameters, and now we're talking about trillion parameter models. So as models get bigger, the performance become better, but also their latency, like the inference latency, it take longer for this model to make predictions. So one of the biggest problems for using machine learning, this is large model in production, is that it takes too long for BERT or GPT to make predictions. So I think one obvious non-solution is just not try to make predictions in real time. Like if you don't do online predictions, there will be no online predictions latency. So a lot of companies are doing what they do is called batch predictions. So we generate predictions offline. and then you store on this prediction somewhere like in a SQL table. And whenever users put a query, you just like try to pull out pre-computed predictions from the table, so you don't have to do predictions online. And batch predictions have worked pretty well in many cases. Even companies like Netflix are still doing batch predictions for their recommendation system. So whenever you go to Netflix, you will have see all the recommendation generated for you, and this recommendation are not generated real time, but they update maybe like every few hours, depending on the specific specification from Netflix. But if you refresh, the order of rows might change, but the exact movie recommendations won't change. So there's a couple of like problems with batch predictions. The first is that you need to know exactly how many predictions you generate. So the input space has to be finite. So in case of recommendation system for Netflix, so Netflix knows exactly how many users there are to generate recommendations for. And if there's a new user joining, they just might generate some generic recommendations, like maybe most watched movies or something like that. The second problem is that it can't really adapt to changing interest. So say like you have been on Netflix and you are having a lot of horror movies lately, right? And so when you go into the Netflix home, you will see a lot of recommendations for horror movies. But you're like very happy today, and you want to see like some comedy. So you go like search for comedies, you go to comedy category, you see, and you could think that Netflix should adopt or like interest now, right? But no, like you won't get new recommendations until Netflix generates the next batch of predictions. So for many companies to continue doing batch predictions, they force the prediction space to be finite by making it discrete. So first of all, TripAdvisor, if you go to advisors, first they make you like choose a metro area, for example, San Francisco or New York, and then you choose another category in a restaurant, a hotel. If you try to do something like different, like input some like free range query, like high rating Thai restaurants in Hayes Valley, you will get something like results that really not relevant at all. Whereas if you enter the same query into Google, you get like slightly better results, but still not perfect, I think. And I would argue like one of the reasons that it makes the results better on Google is that Google does real-time predictions. So another benefit of online predictions is that you're able to use not just static features, but also dynamic features. Static features are something static, for example, age, gender, neighborhood, job income. Of course, they're not static as in they never change, but like they're slower to change. Dynamic features are something that's happening right now. For example, what are you reading right now? What are you watching right now? What are you interested in right now? So this can change because and online prediction will allow you to use this dynamic features. So to do online predictions, you can need two things. First, you need fast inference. You need a model that can make predictions in the order of milliseconds. And second is that you need a real-time pipeline, which means a pipeline that allow you to like take in data, process data, input into a model, and return predictions in real time. So for the first part, fast inference is something that people have been working for in the last few years, and there's a lot of research on it. So there are three ways to make a model do inference faster. First is that you make the models faster. The second is you make the model smaller, and usually when model is smaller, it runs faster. And third is to make the hardware more powerful. So make a model faster. You can make a model run faster by like first of all, like fusing operations, write specific kernels optimized for different hardware like GPU, TPU. I think one example of TensorRT is doing pretty well inference optimizations. Making models smaller is also known as model compressions, and there are so many different techniques that people can use. And one of the most popular techniques is quantizations to reduce the precisions of the more not precisions in like performance, but precisions as in like floating point bit. So usually if you store a normal float as a weight, so they take like 32 bits. But if you reduce like by half, then you only need like 16 bits. And some companies are doing integer, so they're only 8 bit. So you can reduce the model size. And for also like smaller bit numbers also require less and so do computations faster as well. And other techniques like knowledge distillations is student-teacher techniques when you train a small model to mimic the behavior of a larger model. So there's so many different open source project for this, and I think there's one example. You can see in a Fourier Tomorrow compression open source project. And if you're interested in how this model compression is being used in productions, I would highly recommend you read this blog post by Roblox by how they apply different techniques and they're able to reduce the latencies of their bird model like 30 times. Make hardware more powerful is also another very exciting area. So we are trying to build hardware that make it fast for both training and doing inference on both on the cloud and on device. Here's just some of the examples of startups have raised a lot of money recently. And you can see that they are scattered all over the world and not just in the Bay Area. So the next component of how to do online prediction is slightly bit complicated. So it's a real-time pipeline. So to start, let's see an example of a ride-sharing service. And you want to detect whether a transaction is fraudulent or not. So to make that predictions, you need not just information on the specific transactions. You will need to see any other like users' recent transaction, for example, the last 7 days. Like if the transaction use a credit card, you might want to see like when was that credit card added, the recent transactions, because if the credit card just added a few days ago and it has been like used maybe like 200 times, probably because like people, it's pretty fraud because people are trying to optimize the most use out of that like stolen credit card. So also recent enough fraud to see if there's some new recent trends and people are, some people come up with new ways to scam the system. So a lot. So the question is like, how do we quickly access these features? Because you don't want to like store on these recent features on a permanent storage like S3, because like just reading things out from S3 back to the systems take a lot of time and slow down the systems. So you want to store one of these features in memory, and we call them like in-memory storage. So every time an interesting event happens, like for example, users pick a locations, they book a trip, they add a credit card, they contact a driver, they cancel a trip. So all these events go into the in-memory storage, and it stays there for as long as it is useful, for example, 7 days. And after 7 days, this will either go to like permanent storage in S3, or it can be discarded because it's no longer useful. And what is called like this, it's called stream storage, and there are like several popular solutions for it. And the most popular one is probably Apache Kafka. Amazon has also systems like Kinesis, and you can see if you go to StackShare, there are like 100 companies are using the technology. So you have like all the events into a stream storage, right? And then how do you process them to input into the model? So to make predictions on whether transactions is fraud, you need not only like the features from the stream storage, stream data, you also need feature from static data. So static data is something that has like existed before and stored in some format like CSV or Parquet. And static data is something that is bounded, like you know how big it is. And if you tell like, hey, process on the data in that file, like if static data, you know when the job is done. But whereas streaming data is unbounded, like it keeps always coming, you will never finish. Static data give you static features like age, gender, when a guy was created, the user rating. Dynamic features give you like more dynamic, dynamic data give you, or streaming data give you more dynamic features like locations, the last 10 minutes, recent activities. And the last row, I have this hand waving thing, not because like people are waving at you, it's like, it's like it means that it's a very hand wavy way of explaining things. So you will see it in static data because you know exactly how big it is. So you can use tools like SQL or like MapReduce to like efficiently process things in batch. Whereas in streaming data, you want to process things as soon as they come, so we call them stream processing. And some of the common tools for is the Apache Flink and some of them. And if and so you see there are two different ways of like dealing with data, like with static data and stream data. And we know that like in training currently, a lot of people still train models offline. So you have some massive amount of data somewhere and you train it in batch. So you use batch processing for that pipeline. But whereas in productions, if you serve things online. You every time like an event comes, like a data sample come, you want to make prediction on it. So you're doing stream processing. So you see that one model but two different pipelines, and one for batch and one for stream data. And it's one of the common cause source of errors for productions. So it's especially common when these two pipelines are maintained by two different teams. For example, you have the pipeline for the batch pipelines maintained by the machine learning engineering team who does on the training, whereas the stream pipeline is maintained by the DevOps team who bring model to production. So like changes in one pipeline are not correctly um, replicated in another pipeline and can cause errors, like because they use different features now. If you think in the extreme, actually, so it's very common. You can see that in a lot of companies. Here is a slide of the versions of the Weibo pipeline, so it's the online pipeline and offline pipeline. But recently, Weibo has made a lot of effort, like to use Apache Flink to unify the two pipeline. And there's a new unified, and it has happened like also with Alibaba and Uber and Lyft. So we have seen the difference between stream processing and batch processing. And the next stop, I want to talk about the difference between request driven and event driven. And if this term means nothing to you yet, don't worry, we're going to go talk about it. So at this point, you might have heard about microservices. Microservices has taken the world by storm in the last 6 years. And microservices often go hands in hand with REST API. And REST APIs are request driven. So what I mean is that you have like for REST API, you have the client and the server. And the client send a request to the server to tell the server exactly what to do by request like post and get. And the server responds to the request. So a server has to listen for the request to register. So if the server is down, the client would have to keep resending and resending and resending. So I think let's take a sample of a very simple application with only 3 microservices. So one microservice is to manage riders demand, another to manage driver, another manage the price optimizations. So the price demands on demand and availability. So you would need to ping both services for the rider demand and the driver availability. And then as a driver management microservice would need to get the demand from the rider to see like how many more drivers need to mobilize and need to ping the price optimizations to see what search charts they can use to incentivize drivers. And you see like it's very complex. So there's like a couple problems. So first is just like because every service does its own thing, it's really hard to map data transformation through the entire system. And if something goes down with one of the system for the price optimizations, you can need to trace to like A and B to see like how it affects the performance of C. And it's very, very difficult to do with the request driven microservices. So what if we get rid of all the inter-service communications by this model? So owner services can just publish own events in their service into a stream. So and owners of services who want information from there can just like subscribe to the stream and pick out what information it needs. So now all the data flows through the stream. You can actually create a dashboard to monitor how data transformation through the entire systems. And also like and this is what is Kafka is doing, and this model is called pops up. It's not the only architecture for stream, but it's a pretty popular one. So you can see that a lot of companies are doing this, but I think there are a lot of companies are still not doing it. So there's several barriers to it. So first, as companies don't see the benefits of stream processing yet. So the system might not be at a scale where data transferring between services can be a problem, or like best predictions have the score 5 for them, and they have never done online predictions before, so they have no idea how online predictions can improve the performance, and therefore they don't even try. So there are several different other reasons, like it's high in initial investments on infrastructure. So if the company has been doing best predictions and they want to switch to stream processing or online predictions, we need to require a lot of investment in infrastructure. Not a lot of companies are willing to do it. It also is another mental shift. So if you get people from academia, they only used to do things in batch, and now they work with stream data. It can be very disorienting, like what it means to like for it to never finish. And also tools for online predictions like Kafka and Flink. They are built on Java, and a lot of machine learning people are really comfortable with Python, and it might feel like a little bit like squeezy to like to have to switch to Java. So for the next part is online learning, and this part's gonna be quick, mostly because we're out of time. So I want you, like, before we go in, I want you to make a small distinction between online learning and online training. So by definitions, online training is like to learn from each incoming data point, and very few companies actually do it because it suffer from catastrophic forgetting, and so it can get very expensive. As in, like, why using a very big hardware to use like to learn from just one single sample. So in practice, I have seen this a lot of companies who do online learning do it in micro batches. So you learn from so you can wait for like incoming samples, and you can get like maybe like 100, 200, 500, and then learn from it. And then you evaluate after a certain period of time, for example, like 5 to 10 minutes. And you need there are two different types of evaluations. So first, of like evaluations, like to make sure that like this model is not doing something like is like really stupid. And then because the point online learning is that you can adopt the system to changing environment, like first of all changing preferences. So you would need to evaluate on the changing environment as well, so you can't just rely on a static test set. So companies do it by doing like by farm it out to actual users and see how it affect like performance with actual users. And it's a very complex system. A/B testing is complex because you're just not testing within two models, but we test among many different versions of a model. So online learning also, that doesn't mean like you don't do offline learning. So a lot of companies are still doing online learning in tandem with offline learning, and they try so it can give you like a more stable version. Here's an example of like Weibo. Here's another talk from the same talk I referenced before, and their iteration cycle right now is about like 10 minutes from like getting new online dynamics, new features to like evaluating and deploying. So they're like, so the biggest use case for online learning as I see right now is recommendation systems. One reason is that recommendation system is has very natural label. So if user click on something, it's probably like a good predictions. So you don't have to wait for like humans or domain experts to like label the data. You can just get data like on the go. However, not all recommendation system need online learning. So for things that like have very fuzzy preferences that like change slowly, like houses, cars, flights, hotels, you probably don't want to learn continue learning because it's gonna be a waste. However, preference for a lot of things can change very quickly, like especially for online content like videos, articles, tweets, stuff like that. And for that, you want to learn user preference continually. And also because preference for online content change also means that like advertising system will need to also learn continually as well. And you can see online content and advertising everywhere. So you can see the uses for online learnings can be like everywhere. Other cases, for example, like rare events. Think about Black Friday for shopping. Because Black Friday happens only once a year, there's no way you can get enough historical data to learn what the users gonna do on Black Friday this year. So you will need to learn about user behaviors that day on the spot. Or you can also have you deal with cold start problem. When you ship an app to an users, you don't have information that user yes, you don't know what they like. So you will need so if you wait until like the next times or you learn the tuning system and ship the new model, it might be like too slow. So you want to continue to learn as a spot to get the preference of the new users, and it's similar with on device. So on online learning, it's very challenging. It has a lot of theoretical challenges. So first, that it flip a lot of things that you learn about machine learning on its head. So first of all, if people who have learned machine learning in school, we probably have heard some sort of this like similar version, like train a model with a sufficient enough for a sufficient number of epochs until conversions and evaluate on a static test sets, right? So in online online learning, there's no epoch. Like you only see each data point at most once. Like the data points you don't even see at all, and there's no conversions because there's no static distribution to converge to. Like it's always kind of shifting, and there's no static test set because you actually have to test the productions and not you can't rely on a single test set to evaluate the model anymore. If you are interested in learning more about the topic, I'm actually teaching a course on machine learning system design at Stanford, and the material is going to be online. And you can also get in touch with me via Twitter or my email or website. And I'm going to be jumping to Q&A sessions now. Thank you very much. Bye-bye.